Hello everyone, my name is Marco Riani.
And my name is Anthony Atkinson.
With this video we'd like to talk about chapter 1 of our new exciting book.
The purpose of this chapter is to illustrate the difference between the standard approach to robust statistics, which we call static, and our dynamic approach, which uses modern computing techniques. For many centuries, scientists have been worried about accuracy of their observations and disparate observations, or what we nowadays call outliers. The modern theory and methods of robust statistics started to crystallize in about 1970, particularly a group of people gathered by John Tukey. The first publication was a book in 1972 by David Andrews and John Tukey and a number of other people, which has come to be called the Princeton Robustness Study. This book considered the simple problem of estimating location in a single sample, perhaps from the normal distribution and certainly contaminated. The general feeling then was that the robust methods would expand to cover time series, regression, and so forth, and that eventually John Tukey hoped or intended that computer packages should produce the robust alternative as the default, as opposed to, for example, least squares. However, once these methods started to be of interest, there were a large number of developments, and it very rapidly became clear that there was no single robust method. Perhaps this is a reason why these methods have not been adapted so quickly as would have been expected. Our book is about developments of robust methods that we feel encompasses, through the monitoring approach, all the previous work, so that the programs that we present can all be used to do static analyses or, much more importantly, dynamic analyses. So we start where the Princeton Robustness Study started, with the analysis of a simple single sample.
In chapter 1 we introduced the basic estimators of location, mainly the mean, the median, and the trimmed mean. Trimmed mean has an important parameter, alpha, which is the proportion of the most remote observations that you want to exclude. As concerns the estimate of scale, we concentrate on the standard deviation and the median of the absolute deviations from the median. Analysis of MED enables us to introduce and recall the so-called consistency factors. These consistency factors play a very important role in the analysis of robust statistics. Let us start with a very large sample of 20,000 observations. For this sample we compute the MED, and then we repeat the analysis for 100,000 samples. And then we take the mean of these 100,000 values of MAD. So the mean of these 100,000 values of MAD is, in this case, a number which is very close to the third quartile of the standard normal distribution.
This is the theoretical value that is obtained for very large samples using the inverse of the cumulative distribution function of the normal distribution.
In fact, norm inv 0.75 is 0.6745.
Our interest in calibrating the MAD is that we need an estimate of sigma, and it is not clear that the MAD immediately gives an estimate of sigma just from the quartile of the normal distribution. So we need to find its theoretical value and then check how this works for smaller samples rather than for the value for an infinitely large sample.
In other words, if the data come from the standard normal distribution, if you have a very large sample and then you take the MAD, then you divide your MAD by 0.6745, you obtain a value which is equal to 1. You can divide your MAD by 0.6745, or you can multiply the MAD for the reciprocal of 0.6745, which is 1.4826.
Which is what on page 7 we call the consistency factor.
Now we want to check empirically what is the value of this consistency factor for a sample size which goes from 5 to 100. So we run a small simulation study for these values of the sample size. We have 10,000 simulations, and you compute the mean of the MAD for these 10,000 simulations. Now we want to plot our consistency factor.
The bottom horizontal line is the asymptotic value, that is, of course, constant over the whole sample size, and then we see that even for samples of size 100, a slightly larger consistency factor is needed, and as the sample size reduces, a larger and larger consistency factors are needed to, on average, get an unbiased estimate of sigma. There are two things about this, really. One is that in the book, we did it across 100,000 simulations as opposed to the 10,000 here. So the jaggedness in the line is not so apparent in the figure in the book. If you were to follow Marco Riani's suggestion and reproduce this plot for 1 million samples, we expect you would find complete smoothness and no little jumps around at all. At the sample size of 100, the difference is not probably very large, and in many of the simulations that we do in this book, we find that about 100 is the lowest ever value we get, where such things like consistency factors or distributions or parameter estimates have something not too far from the asymptotic distributions. So the basic idea of this piece of monitoring is that we have some quantity in the estimate that we don't really know how to judge. The size of alpha is usually just taken to judge what we believe to be the level of contamination in the sample that we're looking at. Instead of just using the prickling of our thumbs in order to decide these things, we have used this monitoring plot, and we can see what is the effect of changes in the value of alpha on the inferences that we get.
Now we start with the analysis of our first data set of income data.
We look at a sample of 200 observations on income taken from the United States Census Bureau.
As you can see from the left panel, the data are positively skewed.
The right-hand panel of the figure shows the box plot for these data, and we can see that according to the box plot, there are a large number of outliers represented in red.
This is mainly due to the fact that the data are rightly skewed. Given that these are income data, it is likely that these data have to be transformed
in order to get to something like normal or symmetric distribution.
In order to do a preliminary analysis, we compute the box plot for 4 values of the transformation parameter according to the box-Cox family.
In this family, lambda equals 1 is no transformation, lambda equals 0.5 is the square root transformation, lambda equals 0 is the logarithmic transformation, and lambda equals minus 0.5 is the inverse square root transformation. There is an interesting progression in these panels. We have already seen that when lambda equals 1, the original data, the box plot showed a lot of outliers and the whole thing was highly skewed. If we move to the square root transformation, the number of outliers is reduced and the central box is more symmetrical. For the log transformation, everything is virtually symmetrical with just one red dot lying outside the hairs of the box plot. And if we then go to lambda as minus 0.5, we have, as it were, transformed too far, and now the left-hand tail of the distribution is too long.
Therefore, from this plot, lambda is equal to 0 seems to be the best value of the transformation parameter.
Which is in a way very comforting, as this is the standard value for dealing with income distributions that is used by economists.
Another test which is usually used to understand what is the best value of lambda is the so-called score test.
This approximately normally distributed statistic will have a value close to 0 if the correct transformation has been found, and will have large values away from the correct transformation, which is indeed what we see in table 1.1.
You can see, in fact, that the log transformation is the only one which has values in the interval minus 2 and 2.
Further details of response transformation in regression are in chapter 6 of the book.
The next step is to compare the location, the dispersion statistics for the original and logged data. From this table, which is table 1.2, we can see that while the difference between the mean and the median is very high for the original data, this difference is negligible for the logged transformed data. Same thing for the difference between the standard deviation and the MAD.
Although for the standard deviation estimation, the difference is somewhat less severe.
Then we have the trimmed mean, and the trimmed mean depends on the proportion of observations that you wish to trim. In figure 1.4, we show the value of the trimmed mean as the trimming proportion alpha goes from 0.5, in this case we have the median, to 0, and in this case we have the normal mean. Which is the best proportion of alpha? You can see that there is a sort of monotonic behavior, that is, your trimmed mean increases as alpha decreases. So there is no way to say that 0.3 is better than 0.2 or is better than 0.4. The score test that we have seen before is not robust to the presence of particular observations. And in the case of transformations, we need to know whether the evidence for a particular value of lambda depends on the presence of particular observations or it is spread throughout the data. Now we show you monitoring plot of the score test, and we call this plot the fan plot because
it has a shape reminiscent of the fans carried by Japanese ladies. Let us start with the center of the plot. We see that the trajectory for lambda equals 0, the log transformation, lies throughout within the approximate 99% bounds for the value of the statistic. If we move to plus 0.5 or minus 0.5, we see that pretty symmetrically they go outside the central band towards the end of the search as evidence increases that these are not satisfactory transformations. The same is true, but even more so, for the reciprocal transformation and for lambda equals 1, that is no transformation at all. We consider this a paradigmatically well-behaved fan plot. There is clearly a satisfactory value for lambda, and all the other values we consider are rejected as plausible transformations.
An additional benefit of this plot is that it enables you to understand what is the percentage of observations which is in agreement with a particular transformation. For example, you can see when for 0.5 the value of the trajectory starts being out of the thresholds. Therefore, the univariate analysis of the income data for this dataset shows that the log is the best transformation, and this transformation is diffused throughout the data. And there are no influential observations for this transformation. Now we move to the second example. The second example is still referred to income, but in this case the dataset refers to a municipality located in north of Italy. Also in this case we have 200 observations. As we did before, we now compute the same score test for a set of values of lambda which are -2, -1.5, the inverse transformation lambda is equal to -1, then the reciprocal square root, and then log and none. According to this table, the best value of the transformation parameter seems to be -1.5. This is a bit strange for income data to end up with the value of the transformation parameter which is -1.5. Doesn't have an economic interpretation. Now, as we did before, we compare the statistics in the original scale using the inverse transformation, and then we also have the value of lambda is equal to -1.5 because that was the best value according to the score test. Once again, this table is static. From this table, it is not possible to understand whether there are particular observations which play a very important part in the analysis of transformation, and or if there are outlying observations.
So we notice that in the original data, that's the untransformed data, the mean, the trimmed mean and the median are not very much difference, with the trimmed mean and the median being close together. There is, however, an appreciable difference between the standard deviation and the normalized MAD, something like threefold. If we then go to the transformed data, there is a much less difference really in the estimates of the mean in either the inverse transformation or lambda is -1.5, but there is still a more appreciable difference in the two estimates of the standard deviation.
This suggests that it is not enough to say that the robust estimate is very close to the non-robust for a particular transformation, because the fact that this difference is small may be due to the presence of atypical observations. And this table is once again a static way of looking at the data. We have to understand, as we have done before, what is the effect that each unit exerts on the value of the transformation. And similarly to what we did before, now we compute the Venn plot. And we see now that the Venn plot in this case is much more complicated than the one that we had seen before.
In particular, for up to about a sample size of 160, trajectories are somewhat jagged, but they all lie within the 99% bounds. However, towards the end of the search, where we might expect outliers to be entering, we see that there is a huge change in the significance of the various statistics for the various parametric estimates. And this explains why -1.5 showed up when we analyzed all the data together. But you can see from this plot that the red dashed line goes out of the envelopes, and then the trajectory folds back in at the very end, misleadingly giving an implausible estimate.
So let us come to the conclusions and to the message that we want to give in this chapter.
Our message is that in order to understand what each observation is telling us or doing to the parameter estimates or whatever we are actually looking at, we do need to use a dynamic method such as that we have used in the fan plot combined with the forward search that responds, as we have seen in the last plot, very strongly, very quickly, very powerfully to some strange features of the data. Later on, we will need to try to discover methods to indicate what exactly these observations or why exactly these observations are causing such a change from the general overall picture. This is not available at all from the static tables of conventional robust or non-robust analyses.
Thank you for watching, and we hope that you enjoyed this video, and then we hope that we have
whetted your appetite for the rest of the book.
Okay. Thank you for watching.